Cyclotrons and electric fields. In this video we'll be talking about the operation of cyclotrons, and in particular the electric field between the Ds that accelerates the particles. Sometimes charged particles need to be accelerated to very high speeds in order to study their components, and this is also used in a wide range of applications such as medicine and nuclear physics. Now, the energy that the particles are required to get to can be in the order of giga electron volts, but if a machine had a voltage that high, it can be very dangerous, very expensive and difficult to make. A better way of doing it is to have a lot less voltage, could be 1000 volts for example, but have the particle pass through 1000 volts multiple times. This will allow it to reach the giga electron volts, but a lot more efficiently. The more energy that you're required to get your particle to get to, the larger the cyclotron is needed to be. This could be up to 17 meters in diameter. So cyclotrons are a device that accelerates particles to high speeds by utilizing electric fields and magnetic fields to get the particles to cross an electric field multiple times to increase its energy each time. And the magnetic field, which we'll learn in a later video, changes the direction of the particle. So that was just a little bit about the operation of a cyclotron, but I want to go through the components of the cyclotron in a little bit more detail. So an ion source is located in the middle of a cyclotron, and this creates the charged particles of concern. So the ion source is just a heated filament that creates electrons in that space. So electrons come to the top of a metal and they leave the metal. Now the charged particle being created between the two Ds will be attracted to one of the Ds based on that charge and accelerate towards it. So the Ds are just two hollow semicircular containers that are made from a non-magnetic material, and they have an open diameter so ions can pass freely between them. There is no electric field inside the Ds, but there is an electric field between the Ds. So the electric field exists just in this section here, and ions are free to pass through here and here, being open faces, and it allows the ions to move freely throughout this area. The whole apparatus is contained in an evacuated container, meaning there's no air molecules for the ions to crash into. So a little bit more about the operation of a cyclotron. When the ions are created, they will accelerate to one of the Ds. One of the Ds will have a positive charge, one will have a negative charge. So depending on the charge on the particle, it will accelerate in the appropriate direction. Once the particle is within the D, there is no electric field acting on it, only a magnetic field, which we'll discuss later. This magnetic field allows the particle to turn. So in this example here, if we start at the beginning, the particle will turn within the D, and then once it is between the Ds, it will accelerate again due to the electric field. As the speed of the particle increases, the radius increases, and this forms the spiral path of the particle. Once the particle enters one of the Ds, the electric charge on the D is reversed. So when the particle passes between the Ds again, it accelerates to the other D. And this alternating potential difference that's applied to the Ds allows it to continually accelerate as it is in the cyclotron, resulting in that increasing speed that we're looking for. Sketch a 3D model of a cyclotron and label the components of ion source, Ds, evacuated container, and the magnets.